Okay. So everybody, welcome to today's math seminar. So today we invite our new colleague, Yalong Cao, and he had been working in IPMU of the University of Tokyo until recently, but he joined us last month, in the middle of the last month. So in this talk, he is going to explain about Yamil's theory and enumerative geometry on Calabi-Yau fourfolds. So yeah, and yeah, I think he is going to explain some introductory things in the first part at least. But yeah, if you have any question, please feel free to ask anytime. So Yalong, please start whenever you are ready.
Okay. Yeah. Thank you very much for the introduction and the invitation to this wonderful seminar. So actually, I want to spend most of the time on this introduction to this Yamil theory and also connections to individual geometries. In the very end, I will mention some very briefly some of my my research on Calabi-Yau fourfolds. So let's start. So I'm interested in gauge theory. So gauge theory is named by Hermann Weyl about 100 years ago. So in physics language, this is a field theory such that the Lagrangian is invariant under some local transformations of Lie groups. So when this Lie groups is the simplest one, this is a commutative one. This unitary group of this Abelian case. Then this gauge theory is the most important example is this Maxwell's theory of electrodynamics, so which goes back to 19th century. So when this group is non-abelian, so this is introduced by Chen-Ning Yang and Robert Mills to understand the strong interactions in particle physics in 1954. So after that, after this groundbreaking work of Yang and Mills, so gauge theory is also called a Yang-Mills theory. So I just use a Yang-Mills theory to stand for gauge theory in this talk. So Yang-Mills theory actually can be described by the language of modern differential geometry in a very compact way. So we start with a manifold X. So this is a smooth manifold. So possibly with some extra structures like a G, this is a Riemannian metric. So J is a complex structure and omega is some symplectic structures. So we consider a family of vector spaces parameterized by points in X. So this is really called a complex vector bundle. So for convenience, we choose some Hermitian metric on this vector bundle, which is fiberwise is just a Hermitian metric on this vector space. So given this data, this is equivalent to say that we are given a principal UR bundle. So then let's recall what is a connection. So a connection is on this bundle E is actually by that definition is a C-linear map from the space of a smooth section on E to the space of smooth section of this bundle E twisted by the cotangent bundle of X, satisfying this so-called Leibniz rule. So here F is a smooth function and S is a section of this bundle E. So we multiply this is still a section. So we can apply this dA, this operator dA on this section. Then you should satisfy this equality that so this is like a Euler Leibniz rule in differential calculus. So we first take a derivative of this function, which is the ordinary derivative, and then we tensor with the section. And the second part is this function times the operation of this dA on this section S. So this is the Leibniz rule. So any such C-linear map satisfying this condition, we call this a connection on this bundle E. So so notice that because we have this term, so this map dA is not linear with respect to this smooth function action on the space of sections. However, we notice that if we choose a if we choose a two connection, we consider their difference, then it's actions on this F times S behave like this C infinity X linear. So C infinity X denotes the set of all smooth function on X. So literally, this means that we can take out this F before in front of this operator here. So this means that the difference of any two connection on this bundle becomes a tensor. So it becomes a section of this bundle. So which we also write as this omega 1 X endomorphism E. So omega 1 is just the space of differential form, degree 1 differential form. So this means that if we fix some base connection, dA0, there's no canonical choice, but let's fix one connection, then the space of all connection, so let's denote this A to be the space of all connection. So then this is identified with the space of all this bundle valued differential form. So this is quite very, how to say, very well understood objects, sorry. This is very well understood objects. So you don't need to be afraid of these connections if you don't know this concept before. But anyway, this is just up to fixing this base point. This is just this vector space. Okay, so then given a connection, we can talk about what is the curvature of this connection. So the curvature is basically, we consider the composition of this connection to itself. Then this becomes a map from the space of section to the space of this section traced by wedge 2 of this cotangent bundle. So this is a two form. This is a bundle value two forms. So by easy computations of this, based on this Leibniz rule, so we see that this curvature as a map from this space to this space is also a C infinity X linear. So this is by easy manipulation. Then we see that the curvature is also a bundle value two forms now. So now connection is bundle value one form, and the curvature is bundle value two forms. So we have connection and we have a curvature. So we want to talk about what is the isomorphism of these connections. So let's introduce this so-called gauge transformation. So basically, this is just a isomorphism of this smooth vector bundle to itself. So I wrote here, which are covering the identity on the base X. So in your equivalent way, this is a section of this endomorphism bundle, such that at each point on X, this is an isomorphism of linear space. So now this U acts on space of section, then also it acts on the space of a connection by conjugations. So it's easy to track that by this definition, then this action is also after this multiplying this gauge transformation. So this is still connections. So,
so may I ask a question, please?
Yeah, please.
So in the definition of gauge transformation, you say that the restriction of U onto X is isomorphism.
Yes.
Don't you need to assume that it's an identity? Is it enough to say that it's an isomorphism?
Yes. So here, so this is a section of this bundle, endomorphism bundle E. So this means that at any point X, any point x, this is basically a
it's a small x. It's a small
space.
x. Not large x.
Yeah,
but the
small x.
Sorry.
Yeah.
So, yeah. So, yeah. Of course. Sorry. Yeah.
Okay.
Yeah.
So
my question didn't make sense. Sorry. Yeah.
Okay.
Okay.
Small x is in capital X.
Yeah. Okay. Thank you.
Okay. So so then we introduce what is called Yang-Mills energy. So Yang-Mills come back again. So for any connection A, the Yang-Mills energy of this connection is defined to be the norms, this L2 norm of this curvature and the integral on X. Okay, so this is the number, and this becomes sorry, this is a function on X, and this is the volume form on X, which we can do integration. So one can easily track that this Yang-Mills energy is invariant under this gauge transformation. So this Yang-Mills energy descends to the, so this Yang-Mills energy descends to the space of all connection modulo gauge transformation. Okay. So then the Yang-Mills connection is very naturally.
So sorry for disturbing again. So
yeah,
I'm
no
not
problem.
so familiar with the intuition of physics, but why is it called energy here?
Oh yeah, because why this is called energy.
Yeah.
So we can consider so this as some parameter space. So we want to construct some so first of all, energy, I think is you can, if you can construct some non-zero how to say non-negative functions on some parameter space, you can naively speaking, you can say this is some energy. Yeah, because we in a very intuitive way, maybe the energy should not be negative. So
okay.
So you can also call this a Yang-Mills function. Yeah. Anyway. So when I say energy, maybe because the key point here is this is always non-negative. Yeah. Yeah. You can also say Yang-Mills functional.
And one other thing, sorry. So what was small c? What was small c? Maybe I just didn't. I just missed it. What was small g? Yeah.
Oh, small g. Sorry.
Small g.
So when I say volume form, this is usually with respect to a choice of remaining metric. So this g is a remaining metric.
Remaining metric. Oh, okay. Okay.
Yeah. So this volume form is determined by the remaining metric. Yeah, because for example, if you scale the metric, then the volume becomes also scaling.
Okay, thank you.
No problem. So yeah, so now we see that on this parameter space we have some functional. We have some maybe energy. So we want to find it's natural to find the minimizer of this energy, but this is really not very easy to do. So like what we do in the when we learn calculus, if we have a real value function, we want to find the maximum or minimum of this function as some maybe closed interval or whatever compact space. So now this space is an infinite dimension. So because this A is modeled on space of bundle value 1 form, and this gauge is modeled on a space of bundle valued 0 form. So this is an infinite dimensional space. So usually it's not easy to find a minimum, but we can like motivated by this differential calculus, we can talk about what is the critical points of this Yang-Mills energy. So we do just variations of this thing. We want to find the critical points. So the critical point of Yang-Mills energy, this Yang-Mills function or Yang-Mills energy is usually referred as Yang-Mills connection. So this is basically a connection A satisfying this Euler-Lagrange equation. So we have this curvature of A, and we apply this star operator. This star is the Hodge star operator. So let me write here. So FA, recall this is a bundle value 2 form. So this star is a Hodge star operator maps to a bundle value n-2 form, where this dimension of x is n. So then we apply this star operator to this curvature. So this becomes a differential form here. Then we can extend this this operation of dA on this section. Previously, we only defined this action of dA on space of sections, but we can easily extend by a Leibniz rule to this space of all differential forms. So this is the meaning of this equation. So so critical points of this Yang-Mills energy, which can be verified, satisfying this equivalent satisfying this equation. So now we call this such connection a Yang-Mills connection. Okay. So Yang-Mills connection is a connection satisfying this equation. This is definition. Okay. So until now, this is a rather general setting. So we can start with any smooth oriented compact manifolds, closed manifolds of any dimension. So we can talk about this Yang-Mills energy, Yang-Mills connection, if we fix a metric. So now I want to specify the dimension of the base manifold. So this comes to the story of so-called anti-self duality. So actually 4 dimension, so this is a real 4 dimension, is a distinguished context for Yang-Mills theory. So this is because, so if we consider this remaining 4 manifold, so the structural group of this manifold is this group SO4. So the Lie algebra of this SO4 is not simple, so it can be decomposed into the direct sum of the Lie algebra SU2 plus this direct sum with itself. So this is quite a remarkable phenomenon, and it can be reflected at the level of differential forms like this. So we consider this space of 2 form. So we can define this Hodge star operator maps these 2 forms to, so you can see here, maps 2 forms to n-2 form. But now the dimension is 4, so it maps back to the space of 2 form. So in a way that this becomes a endomorphism of this infinite dimensional space. And you can easily track that this star is an involution. So in the sense that this square becomes an identity. Okay. So then it's a standard trick in the linear algebra. So if you have the involution, you can decompose this space in terms of this eigenvalue decomposition. So here I write this omega 2x in terms of omega 2 plus x and omega 2 minus x. So the elements here, so alpha belongs to omega 2x plus x is exactly, is by definition, this star of alpha is alpha. So alpha belongs to omega 2 minus is the same as a star alpha equals to minus alpha. Okay. So this is quite elementary thing. So by this trick, we can define what is called anti-self-dual connection. So anti-self-dual connection is a connection such that this self-dual part of this connection is 0. Okay. So here, so you may be confused a little bit here because sometimes I write this star from this with this bundle value, but sometimes I didn't. But I want to say is that so extension of this star operator from differential form to bundle differential form is just a standard manipulation. So it's nothing tricky here. So you can, in any case, if you take this E to be trivial, this recovers this case. Okay. So okay. So now I want to say curvature is a bundle value 2 form. So we can similarly decompose this bundle value two forms into plus and minus. Then we can make sense what is this plus side of this curvature tensor. Okay, so is this part clear?
Yeah, and
okay,
for me it's fine, but maybe yeah. So shall we have some? Yeah. So is there any question from the audience? No?
Yeah. Is there any questions so far?
Any kind of question about, for example, about So let me ask one question about this more. I mean, more not math things, but I mean, so. So could you explain only a bit about so this is about four-dimensional theory, but so is there a similar theory for other dimension?
Yeah, this is a very interesting question. This is a very important question. This is the question we'll go through my talk today. Yeah.
Okay.
Yeah.
So you're going to explain about it. Okay.
Yeah, I will mention the
okay.
other dimensions and is possible. Is it possible to extend to other dimension and yeah, the possibility and the not possibility. Both cases. Yeah, I will mention. Yeah.
And another thing. So so the what kind of thing is a grand goal of this entire theory?
The goal of this entire theory.
Yeah.
Yeah, that's also a very good question, because the I think the goal is, how to say. So Yang-Mills theory is at the beginning. So as I said, this is comes from physics theory. So in physics world, this has a very clear goals to solve some problems in this particle theory. But in the mathematical side, I think people are interested in this. People are interested in these things because so first of all, the theory is very beautiful. And second, how to say, maybe this is the most important reason. Yeah, I think in mathematics, if the structure is very beautiful, then it deserves study. And yeah, I will mention why it's so important to study Yang-Mills theory. And also regarding to your questions, I think through my talk, I think I want to convert the thinking that it's interesting to set up how to think about the theory by ourselves. So sometimes we are the people who may invent the theory. So through my talk, you will see, okay, so what should we look at gradually? Yeah, after my explanation. So at the very beginning, you can say that there's no goal. Yeah, but
I mean,
but after some exploration in this direction, you will see that many interesting structures appears, and also some very important applications appears. Yeah, you will see.
Okay.
Thank
you.
No problem. Yeah. Okay. So similarly, we can also define self-dual connections. So by this minus part is 0. So so how this anti-self-dual connection links with the Yang-Mills connection? So so this is by sorry. So by this so-called Bianchi identity, we have this. If we apply this connection to the curvature, then this is always 0. So this is called Bianchi identity. So from this Bianchi identity, we see that start with a anti-self-dual connection. That means FA plus a star of FA is 0. Then if we apply this DA, so we see that this is always 0. So this implies that DA star FA is 0. So what this means is that any anti-self-dual connections are automatically Yang-Mills connection. Okay. So moreover, there are quite special. So they are actually energy minimizer of Yang-Mills energy. Okay. So this is can be seen by easy manipulation of this characteristic class argument. So let's just quickly look at this. So let's first look at the energy of this curvature. So by this decomposition into self-due part and anti-self-due part, so this curvature, energy of curvature becomes this sum of these two curvature. So by this Chen-Wei theory, so the trace of this curvature square, if you integrate on x, so this is a number. So recall this curvature is a bundle value 2 form. So if we, okay, let me write here. So curvature is a bundle value 2 form. So the square is a bundle value 4 form. So if you take a trace means that we take a trace in this endomorphism E, then this becomes just an honest 4 form on X. Because X is a 4 manifold, so we can integrate this 4 form and get a number. And the theory of Chen and Wei say that although this curvature can be very complicated, but after doing this manipulation, this becomes a topological thing. So this is the second Chen character of this bundle E integrate on X up to some this constant by minus a pi square. Okay. So this is a topological invariance. So also through this decomposition to self-due part and the anti-self-due part, so we can write this as a difference of these energies. So then you can easily see that if you take a difference of these two equations, then the right-hand side becomes 2 of this energy of this self-due part. And the left-hand side becomes the total Yang-Mills energy plus some topological constant. Then you see that because this is energy, this is always non-negative. So this implies that this Yang-Mills energy is bounded below by anti-self-due connections. Okay, so this is the justification of why Yang-Mills energy, energy minimizer of this. Why anti-self-due connection as a Yang-Mills energy minimizer. Okay. So you can also see that. So this special structure gives you Yang-Mills energy minimizers, which a priori is not so easy to find out. But this 4 dimension is quite distinguished, so we can find this energy minimizer. So another key property of this anti-self-due equations is from differential from this differential equations perspective is called so-called elliptic equation. So in a very naive way, we can understand this as we have a space of variables. As I said before, this is a model on a bundle value 1 form, and we have equations which is model on bundle value self-due 2 forms. And we also have because we also need to module the gauge transformation, so we need to do the gauge fixing. So do the gauge fixing requires extra equations in terms of these bundle values 0 forms. So let's maybe forget this bundle value part. So this is not very essential in the discussion. So if you consider the space of 1 form, so at each point on X, obviously definitely this is an infinite dimension, but on each if you fix any point on X, so this is a finite dimensional vector space. So this is a rank 4 because very intuitively we have coordinate x1 to x4 on the 4 manifolds. So dx1 to dx4 gives you this 4 dimensions. Okay. So similarly, you can consider a space of 2 forms. So because 4 choose 2 is 6, so this is a 6, rank 6. So very explicitly, this is written as dx1 wedge dx2, dx1 wedge dx3, and so on until dx3 wedge dx4. So easily see that there are 6 such generator these spaces. Then if you use this self-duality to decompose these two forms into self-due part and anti-self-due part. So each piece, let's say self-due part, now becomes the half of this rank. So it becomes rank 6. So also finally know that the zero form is just one that just the rank is just 1. Yeah. So the important thing here is a very elementary thing. The important thing is 4 is equals to 3 plus 1. So this means that the number of equations and the number of variables are the same. Okay. So this means that if we consider this ambient space of all connection up to gauge equivalence, so this is a priori this definitely an infinite dimensional space. But if we add this equation, this anti-self-due equation, then we can get a finite dimensional subspace. So this is a consequence of this ellipticity of these equations. So this is quite a remarkable phenomenon here. Okay. So so then the interesting thing is that we can study the geometry and topology of this moduli space. Now this is finite dimensional, so mathematicians have a lot of tools to study such space. Yeah. So before moving to this introduction of this developments in this moduli space, I want to make a remark that definitely we don't necessarily consider anti-self-due connection. We can also consider this flat connections. Okay, this is just requiring the whole curvature to be 0. But I want to say that on 4 dimension, this becomes an overdetermined equation because we have the number of equation which becomes 6. So this is bigger than the number of variables. So this means that this too many equations, so this overdetermines. Okay. Generically, if you consider such a flat connection equations, so there's no solution anymore. Okay, so now I want to move to some just words. So there's some stories about the developments towards this moduli space. So in 1978, Atiyah and Hitchin and Singer, so they began to study this moduli space of anti-self-due connections or self-due connections from mathematical point of view. So you see that Yang-Mills theories begins in 1954, but it turns out that after 20 years, so this leading mathematicians began to study such a Yang-Mills theory from mathematical point of view. Okay, so what they do at the beginning is not very difficult. They first considered the so-called formal dimension of this moduli space on the simplest four manifold, compact four manifold. This is a 4 sphere. We call it. We use notation as 4 to denote. So what is the formal dimension of this moduli space? So as I said, so we have this space of one form, bundle value. We have this space of self-due 2 forms, also with bundle valued. And we also have this space of 0 forms, which correspond to gauge fixing condition. So there's some operator here. Let me call this maybe D. So this operator has to do with this curvature and also this projection to self-due part. But I don't write it here to make not to spend your energies on this part. But what I would say that there's some distinguished differential operator D here. So the formal dimension is basically the dimension of this kernel of this operator minus the dimension of the co-kernel of this operator. So by the ellipticity of this anti-self-due equation, so the kernel of this kernel and the co-kernel are finite dimensional subspace in here and here. So it makes sense to talk about their dimensions. So for differential operator like this, so there's a famous so-called index theorem computing such the difference of their dimensions using this truncat of E and A hat and some topological invariants of X. So this is usually referred as a Atiyah-Singer index theorem. So what Atiyah, Hitchin, and Singer did is they compute a formal dimension, which is the index of this operator on S4. Okay. So so this computation also addressing the earlier work by several physicists. This BPST back to 1975. So around the same year, so Atiyah, Drinfeld, Hitchin, and Singer, they actually construct this moduli space very explicitly on S4 and the gauge group SU2 by very explicit data using some linear algebra data. So this is usually referred as a ADHM construction later in both mathematics and the physics literatures. So this has very important influence on later studies. For example, it motivates Professor Nakajima to introduce his quiver varieties, which is very important in this geometric representation theory. Okay. Okay, so you see that Atiyah begins to study this Yang-Mills theory from 78, only after 4 years. So one amazing breakthrough appears. So this is what Donaldson did in his PhD thesis. So Donaldson made the Yang-Mills theory famous in mathematical world by analyzing the geometry and topology of this moduli space. So by using this geometry of this moduli space, he showed that many topological four manifolds do not have smooth structures. Okay, so this is a result which Atiyah said stunned the mathematical world. Yeah, because this phenomenon only happens in 4 dimensions. In all other dimensions, any topological structure admits a smooth structure, but this is not true in 4 dimensions. Okay. So actually, Donaldson's work is built on Friedman's work on classification of topological four manifolds, and there's also deep analytic works by Taubes and Uhlenbeck on this existence of anti-CFT connection and the compactification of this moduli space. Anyway, this is just some names and words. It's not just want to remember their contributions. So it's quite interestingly, you see that around the same year, this breakthrough appears. So suddenly, this so many important works appears in this mathematical development of Yang-Mills theory. So yeah, so I think the interesting thing here is that at the very beginning, people didn't expect that Yang-Mills theory has any impact on mathematical side. Yeah, mathematical structures, but and because I think because a mathematician like Atiyah, Hitchin, and Donaldson, they think that studying such a Yang-Mills theory is interesting, so they just spend time to study such theory from a mathematical point of view, and yeah, interestingly and also luckily that they find important applications to the mathematical world. Yeah. So okay, so final words about 4 dimension is that later Donaldson also introduced his famous invariance called Donaldson invariance, which naively speaking counts a number of anti-CFT connections on 4 manifolds. I will mention this later when we come to Calabi-Yau fourfolds later. Okay, so this is 4 dimension. So so obviously you want to understand the other dimensions. So let me not so be ambitious. Let's just move to 3 dimensions. Okay, so on 3 dimensions there are some very distinguished structures here, because we have so-called Chern-Simons functional. So Chern's name appear again. So Chern-Simons functional is a function on this space of connections. So actually you can also descend to gauge equivalent classes of connections anyway. So it's a map from space of all connections to this real value. the set of all real numbers. So basically, we start with a connection. Then we can consider this connection, wedge this dA, and plus this a cube. So now this becomes a bundle value. This bundle values three forms. By taking trace, this becomes a free form, and then we can integrate on three manifolds. Okay. So what I want to say is that so we should ask ourselves, so what can we do if we are given such a Chern-Simons function? What can we say? Now, I think usually this question is the most important things to start to develop a whole subject. So actually, after study of many people, like Floer and Witten, so the theory we should look at is the so-called Morse theory. So this is what I wrote here. They fit into the setting of a Morse theory. So let's recall what is Morse theory. So we are given a function, smooth function on a finite dimensional smooth manifold M. So let's say this is a Morse function. So this is locally is written like this difference of this like this quadratic polynomial. Then we can define a chain complex from this data, from this Morse function. So the chain group is generated by the critical points of F. So now I draw a picture here. So let's say P1, P2. Also, there are other critical points, but let's say we have two critical points, P1, P2. So we just collect all such critical points that they are finite number of such things. So we just generate a chain group. Then we want to define a differential on this chain group, like what we do in the homology or cohomology theory. We have a group, we want to define a differential. Then the differential is actually very geometric. So the differential is we count the number of gradient flow lines between this linking these critical points. So by some theory, we know that the number of such gradient flow line is a finite number. This is a finite set, so we can exactly count the number of gradient flow lines. So this defines the differential. So having this chain complex, then we can take the cohomology or homology of this chain complex. So this is usually called a Morse homology or Witten-Morse homology, because this is this idea comes from a famous paper of Witten. And the important consequence is that although we start with extra data, this is a smooth function, but the homology only depends on the topology of M. So actually it's isomorphic to a singular homology of M. Okay, so you may ask, so you start with this smooth function, and you do this complicated defining definition of this chain complex, but in the end you recover the known homology, this known topological invariance. Why I should care about this? But the point here is that the important point here is that we give another description, another perspective on how to define this chain complex, yeah, or this homology group. So this change of perspective is very, very important, because this means that we are essentially using this differential calculus, because F is a smooth function. We're using differential calculus to study the topologies. So in 1988, so this is 6 years after Donaldson's work, so Floer introduced Morse homology, just following this perspective. He introduced the Morse homology of this Chern-Simons function. So recall that, so in this finite dimensional case, we have some Morse function, but in this Chern-Simons case, this is an infinite dimensional space. So it's more difficult, definitely, to make sense what is the critical points and what is the gradient flow line here. Okay. So actually, Floer defined this so-called Morse homology of this Chern-Simons functional, but now these people call this credit Floer to call this instanton Floer homology. And the key structure here is that the critical points of this Chern-Simons functional now it becomes flat connections on these free manifolds. So this is just easily done by just doing this variation on this functional. You can see the critical points of this function is exactly a connection satisfying this curvature is 0. This is flat connections. So okay, so then what is the gradient flow line? So the gradient flow line equation is something like here. So basically what we consider is like here. So the critical point now is a flat connection, but we want to consider gradient flow line. So this is a one parameter family of connections on free manifolds, right? Because any point here is a connection. It's a connection because the domain is now A. So now if you want to draw a real line, this is a one parameter family of connection on free manifolds. So this is refers to this parameter T, this is the parameter for this line. If you take a derivative, then this becomes the star of these curvatures. So surprisingly, this has connections to anti-self-dual connections on four manifolds. Okay, so in fact, this is exactly the anti-self-dual connection equations on these three manifolds cross R. So this is four manifolds. So in a way that Floer's theory and Donaldson's theory, they have deep connections. Okay, so then I want to finally, before I move to the complexification, I want to mention this something called the TQFT structures underlying this three dimension and the four dimensions. So okay, so let's recall that maybe let me write here. So recall that on closed, maybe oriented four manifold. So we have this Donaldson invariance, although I didn't give you the definitions. So Donaldson invariance is a count of anti-self-dual connections on X. And on this closed oriented free manifolds, let's say Y. So we have this Floer cohomology, or Floer homology. Let's call this a Floer homology of Y. So these two theories are not unrelated. They are actually related by this picture. So we have this, let's say we start with closed four manifolds, and let's consider one parameter family of such a four manifolds. So the index here is denotes the parameter space. So we can just basically deform the metric to make these four manifolds look like this. So this means, and in the middle, I want these four manifolds to be like the free manifold cross this R. So this is something like a cylinder. Okay, and in the end, I want to break these four manifolds into two pieces. So each piece is a four manifold, but this is not closed anymore. It has some boundary. So the boundary is three manifolds. Okay, so this so looking at this Donaldson and the Floer case, so people propose that like Atiyah and just also Donaldson and Floer, they propose that on this relative case where we have a four manifold with boundary, then there should be a relative theory. Maps means assign this picture to elements in the Floer homology. Okay, then the pairing of these two elements in the Floer homology will give you the Donaldson invariance after smoothing these four manifolds. So this is called the TQFT structures in Donaldson-Floer theory. Okay. So is this clear in this to you guys?
So yeah, it's quite interesting. And
okay.
So is any question from the audience? Maybe so yeah, it's about 4:50. So
so
but
maybe
anyway.
we have a quick break or something.
Yeah. Is it the is it if it is okay? Maybe we can take some
because
break.
now it's about a real case. Just the other half I will want to consider the complexification of the bound
okay.
theory. So maybe it's a
Great,
good point
great.
to have
okay.
5 minutes break or something.
I see. So before going to break, so yeah. So is there any question from the audience? No question? Yeah, maybe, yeah. Anyway, you can ask Yalong during the break if Yalong is here. But anyway, it's okay. So maybe we can take 10 minutes break. Maybe?
Okay, 10 minutes is okay. Sure.
Yeah. So shall we resume then 5 past 5? Then.
Yeah, sure.
Yeah, okay.
Yeah.
Okay. Then let's resume that time.
Okay.
So I will stop recording for a moment.
Okay, let's resume. Yes. Okay. Where am I? Okay. So please ask questions if you have any. So no matter what kind of questions. Yeah. So I think maybe I don't know whether I say too quick or maybe people have already sleep or something.
No, I don't think so. But
okay.
Yeah.
Okay. Yeah, because I think the important thing is that what I want to as I said, I think the important thing is to ask the right questions. But before asking the right questions, so we have to ask questions. Okay. So okay, let me mention what I mean to be a complexification. So previously, what we studied is some Yang-Mills theory on 3 manifolds or 4 manifolds, particularly where this gauge group actually is a unitary group, as I mentioned. So this is some compact group, but it's interesting question that can we do some extensions or generalizations? Okay, so to other dimensions. But the first perspective is that we can try to do complexifications. So complexification, there's some 2 ways to do such complexifications. The one way is to complexify the structure group. In physics term is also called gauge group. From this compact Lie group to some complex Lie group. Okay, and so this perspective is important to because Witten has some interpretation of a Kovanov homology of knots using such perspective. But I don't want to mention this today. So my focus here today is to complexify the base manifolds, not the structure group. So the structure group of our bundle is still a unitary group. So this is a compact Lie group. Okay, so let's start. So previously, our theories are actually on real-oriented 3 and 4 manifolds, because if you remember, we need to define some integrations. So this integration depends on the choice of these volume forms. So this is equivalent to say that this is real-oriented, because real-oriented, if you learn this manifold theory, real-oriented means that we have a global volume form. So locally it's written like a dx1 match dx2 to dxn. So n is the real dimension. So the complexification, so this notion of complexification is that we need to have holomorphic volume form. Okay. So basically we replace this dx1, dx2 to dxn by dz1, dz2 to dzn. So the z1, z2, zn these are holomorphic coordinates of our complex manifolds. Okay, so now complex geometries appears, but not every complex manifolds have a holomorphic volume form. So this is quite different from a real-oriented case, because the most most of real manifold we consider are real-oriented. So actually, real orientation is not a essential conditions, but the complex orientation is quite essential here. So in fact, this complex manifold having holomorphic volume form are called Calabi-Yau manifolds. Okay. So, okay, so let me come to this complexification of this 4-dimension first. So this I just put here as a complex anti-self duality. So now we start with X is a smooth projective Calabi-Yau fourfolds. I always work with the field of complex number C. So this smooth is just a smooth in whatever sense you have in mind. This projective is if you don't study such algebra geometry, you can ignore this projective. It's just say that okay, this is smooth, a compact Calabi-Yau fourfold. Okay. So now the important thing here is that we have some distinguished metric on this Calabi-Yau fourfolds. So this is some rich flat Kähler metric G. This constructed by Yau's solution of Calabi conjecture. And there's some distinguished 4 forms, which I mentioned earlier. So this is the holomorphic volume form. So in this Calabi-Yau 4-dimension case, this is complex. So sorry, this is holomorphic 4 forms here. I call this capital omega. Now we want to extend the story of self-dualities. So originally on 4 manifolds, we look at the space of 2 forms, where the coordinate is dx1, wedge dx2. Now we want to complexify the notion. That means we want to have dz1 wedge dz2, or dz1 bar wedge dz2 bar. Anyway, this is a notation. There's no notation preference. So this means that we consider this space of 0-2 forms. So I want to say again, so 0-2 form means a dz1 bar wedge dz2 bar, something like that. So we don't want to mix the holomorphic part and the anti-holomorphic, just a conjugate of this holomorphic part. Okay. So so we have this star operator. So this is defined on any remaining manifolds. So from this star operator, anyways, because this is a Kähler defined by the Kähler metric, so it preserves the complex structure. So it maps 0-2 forms to 4-2 forms because X is complex 4 dimensions. So you see that the 0 plus 4 is 4, 2 plus 2 is 4, so 4 plus 4 is 8. So this is matches. So now, because we have a distinguished volume form omega, we can contract this volume form, which contract this 4 part. Okay, so then this maps back to the space of 0-2 forms. So by this trick, we can construct involution on space of 0-2 forms. Okay, so this is quite a remarkable structure, special to Calabi-Yau fourfolds. Okay. So similarly, we can couple with a complex vector bundle with Hermitian metric. This extends to an involution on this bundle value differential forms. Then you can easily write down what is a complex anti-self-dual equations. So this is basically, you consider the 0-2 part of this curvature. You consider the not this is 0, but this plus is a star is 0. So this is a direct analogy of anti-self-dual equations on real 4 dimensions. Okay.
So sorry, I have a question.
Yeah, please.
So why should we? Why should the domain of the star 4 should be omega 0-2, not 0-0?
You can also consider 0-0, yeah. But this okay. So this star 4, as I said, this is a composition of this Hodge star with contraction of holomorphic volume forms. So in the ordinary case, so this star operator maps the space of PQ form. Now we have a Calabi-Yau fourfold case. So it maps to a 4 minus P and a 4 minus Q forms. So this is okay.
I see.
Yeah. So in particular, as I said, the complex analogy of 2 forms is not 2 forms, but it's 0-2 forms.
Yeah. So so we can get the involution, right?
Yeah, exactly. Yeah.
Thank you.
Yeah, no problem. No problem. Yeah, that's a good question, actually. Okay, so okay, where am I? So okay, so now we arrive at the analogy of ASD equations on Calabi-Yau fourfolds. So now, as before, we want to module the we want to talk about isomorphism classes of such solutions of equations. So we want to module the gauge group. Okay, so the natural complexification of gauge group is that the the complexification of a gauge group is now just, we call it GC. So this is a gauge transformation which does not preserve metric anymore. So this is just a complex gauge transformation. But very unfortunately, so this group after complexification, just GC, does not preserve these equations. This is simply because this star 4 is not complex linear. So it's complex and anti-linear. So this means that the star 4, if you maps to square root of -1 to some form alpha, this becomes a minus this. So it's complex, not complex this is not complex linear. Okay, so this means that the GC does not preserve the equations. So the way to help this is some well-known things in symplectic geometry or Kähler quotients. So recall that, let's pretend that this is some Kähler manifolds. This is some reductive group, which is a complexification of some Campelli group. So from this data, we can construct the so-called moment map equations, which is from this Kähler manifolds to the dual of the Lie algebra of this G. So in this particular case, this moment map equation is you start with a connection A, then there's a connection A, then we want to map to the dual of Lie algebra. So the Lie algebra of this gauge group is a space of 0 form. So this we met before. So the dual is now becomes the space of 8 forms. So now our curvature is a space of 2 forms. Then we wedge this, as I said, this omega, small omega is the, okay, maybe I didn't write here. Sorry, small omega is the Kähler form, or symplectic form of this Calabi-Yau fourfold. So this third power becomes a 6th form. So in total, this becomes 8 forms. So lives in here. Then there's some infinite dimensional Kempf-Ness type theorem says that this complex quotient is the same as the this symplectic reduction. So this is take some inverse of this inverse of some values in the target of moment map and the quotient by the quotient by this Campelli group. Okay, so so in a way that this is some, how to say, this is some heuristic, is because this is infinite dimensionals. So this result is not actually true, but instead this motivates us to consider the following equation. So instead we consider, so still the first equation is the complex anti-self-dual equation, but now the second equation we replace, we add up this this equation that FA, this curvature, wedge this third power of Kähler form becomes some constant. Okay, then we add this equation, then we can module out the unitary gauge transformation, okay, which preserve the star 4 operators. Okay, so in a way that this solve the problems I mentioned earlier. So this also give a natural explanation that why such a moment map equations appears. So now this C actually this is some constant that does not depend on A. Okay, only depends on the topology of bundle here, but I don't want to specify here. Okay, so the important things here is that this system of equations is an elliptic equation, a modulo this unitary gauge transformations. So this is exactly at the setting of anti-self-dual things in 4 manifolds. So we got some finite dimensional modular space cut out by this system of equations. Okay, so there is an interesting question to construct Donaldson type invariants in this case. Okay, so I will mention this part later in the very end of this talk. So let's move on to the complexification of this real free free manifold case. So this is a Chern-Simons case. So now the title, we call this holomorphic Chern-Simons. Okay, so as before, we know that we complexify the real free manifolds. Now we arrive at Calabi-Yau threefolds. Okay, and let's say this capital omega is the holomorphic free form. And now the holomorphic Chern-Simons is defined by this obvious extensions. So this first term is still this Chern-Simons term, but now this is a free form. But our Calabi-Yau free form is a real 6-dimension manifolds. So this free form cannot be integrated. Okay, so we need the extra free form. But now Calabi-Yau free form, this has a distinguisher, holomorphic free form. We can put it here and do this integration. So this degree matches with the dimensions. So it makes sense to do integrations. So now the new recipes, so the new perspective is, okay, we want to do some analogy as the real case. So the real case, we are essentially doing Morse theory, okay? But now the difference is that the target is the target of this map is not real anymore. It's a complex number. So in a way that we need to find out what is a complex Morse theory. So this fits into the setting of a complex Morse theory. So complex Morse theory is studied many years ago. If it is the classical part is go back to Picard in maybe 19th centuries. And also later developed by Lefschetz in the early maybe 1924 or something. Yeah. So this is usually called the Picard-Lefschetz theory. So let me just very quickly recall what is Picard-Lefschetz theory. So okay, so we still go back to the finite dimensional setting. So let's say M is some Kähler manifolds, which definitely not compact. So we have some holomorphic function on this Kähler manifolds. And let's say this is a holomorphic Morse function. So locally it's still this Z1 square plus Z2 square to Zn square. Okay. So so now the critical points of this holomorphic Morse function is just isolated. There are finite number of critical points. We call this P1 to Pn. And let's call this a critical value to be Zi, which is the value of f at this point Pi. Okay, so let me draw a picture of this this setting. Oh, sorry. So we have this M and we have this C. So C is just a complex plane. Let's draw this critical value here, and let me draw the critical points here. So now the setting of the setting of this complex Morse theory is that we choose a generic points in this C, which avoids all the critical values. Then we consider the fiber of this map F. So this becomes some complex submanifolds or Kähler submanifolds in M, which is in the fibers. Okay, so then we can see that there's some distinguished Lagrangian sphere here. So there's some sphere. So this is a real sphere of middle dimension, which goes to these critical points if you choose some path in the base. So basically, if you start with a path here, we can do this parallel transform of this Lagrangian sphere to this point. Okay. So and for each critical point, it goes to exactly one Lagrangian sphere in these fibers. Okay. So this is why I write critical points here in one-to-one correspondence with Lagrangian spheres in the fibers, generic fibers of this map. And moreover, all these Lagrangian sphere generate the homology group of these fibers. Okay. Then basically the classical Picard-Lefschetz theory studied the topology of M from this information of this intersection of these Lagrangians. and also some monodromy actions from the base. But what's more interesting is so-called quantum corrections to these Lagrangian intersections. So basically, as I said, so critical points are one-to-one correspondence to Lagrangian sphere. So in a way that we can just remember Lagrangian sphere and forget about the setting of Moore theory anymore. So this becomes Lagrangian sphere in some Taylor manifolds or symplectic manifolds. So then definitely it's interesting to study the classical intersection theory, but this modern mathematical physics say that we should look at the so-called quantum corrections, so which fits into this story of so-called Foucault category things. So basically, we want to consider the count of the holomorphic strips, something like this. This picture maps to our fibers, which is Kähler manifolds, such that this two edge maps to this intersection point, and this two edge maps into the Lagrangian boundary, and this holomorphic disk is inside the Kähler manifold, so F inverse Z infinity here. Then the underlying structures of this complex Moore theory setting is that we should have a Foucault Seidel type category or Foucault category, whatever. So I put name Seidel here because it's in this complex Moore theory setting, this actually Seidel makes sense these theories in a rigorous way. So now, what is this category? So very naively, this category has the objects and the morphisms. So the object is exactly the critical points of these functions, which is equivalently the Lagrangian sphere. And now the morphism is defined by some homology group of some chain complex, where the chain group is generated by Lagrangian intersection point. And the differential is defined by accounting these holomorphic strips. So actually, to fit these pictures into our setting, we may interpret the intersection of this Lagrangian sphere from another perspective. So let's look at the picture again. So because our setting means the holomorphic Chern-Simons setting. So you see that in this finite dimensional complex Moore theory setting, we need to consider some fibers of these generic points here, and do this Lagrangian Floer theory in this symplectic manifolds. But the point here is that in this holomorphic Chern-Simons case, this fiber is infinite dimension because M is already infinite dimension. So if you take a inverse of some point here, it's still infinite dimension. So it does not make sense to talk about what is Lagrangian in this infinite dimension setting. And it's not to say consider the intersection of this Lagrangian sphere. So we need the alternative perspective here. So the alternative perspective is like this. So in fact, any point in this Lagrangian sphere comes from solving some first order equations in here. So let's say we start with this point and we fix some tangent direction, something like this. Then we can solve this one parameter family. We can solve this equation that R maps to here, such that this is linking here to some elements in fibers. But if you fix the tangent direction, so solving this equation, you see that in the end, this goes to some points in the Lagrangian sphere. Okay, so this means that if you consider the intersection of these two Lagrangian sphere, so which is some point here, so you basically this is one-to-one correspondence to some broken flow lines like this. Okay, so this means that we replace the Lagrangian intersection point by some broken flow lines linking these critical points. So which certainly makes sense now. Okay. And moreover, the holomorphic strip information here becomes some holomorphic disk between this two flow lines. So given flow lines. So we are counting some holomorphic disk here to replace the holomorphic strip informations. Okay, so this part is maybe sounds a little bit technical, and if you look at this first time, but the key point here is I want to motivate the differential equations I will introduce in the next page. So now we go back to this holomorphic transaminds. So you can do this because we want to do complex mode theory. Okay, so we want to figure out what is critical points, what is gradient flow lines, and what is holomorphic disk. Then this system of equations, these three equations definitely make sense. So if you explicitly write it down, let's say the critical points first, so this exactly corresponds to the so-called holomorphic flat connections on Calabi-Yau freeforms. So an equation, this means that we consider the curvature of connection A, then we consider the 0,2 part of this curvature and require this to be 0. Okay, so this is called holomorphic flat because this is a holomorphic version of flat equations on Calabi-Yau freeforms. So similarly, you can go to one dimensional higher. You consider a gradient flow line between this critical point. So this becomes a one parameter families of connections on this Calabi-Yau freeforms, or equivalently, this becomes a connection on 7 manifolds. So this is so-called G2 instantons on this 7 manifolds, which I will mention G2 later. And then the holomorphic disk becomes so-called spin 7 instantons on this further dimension, this Y cross R2. Okay. So I want to say that now the spin 7 instanton is exactly the complex anti-self dual we mentioned earlier. Because this is the Calabi-Yau freeform, if you give a complex structure here, this is the Calabi-Yau fourfolds. So this is a holomorphic, complex anti-self dual plays a role in the holomorphic disk in the complex transaminds case. Okay, so then it's interesting to construct the Fukaya-Saito type category structures of these holomorphic transaminds. So which is still not constructed yet. Okay, so then after these explanations, so yeah, maybe you have lose your patience. So yeah, anyway, so the natural question is, do the above stories have generalization to other dimensions, like 10 dimensions or 10,000 dimensions, whatever? So the short answer is no. Okay, they're very special. So remember that the key features of all these equations, holomorphic flat or G2 or whatever, so these I didn't explain, but I explained the complex anti-self dual. So these are elliptic equations. So the key point is that the ellipticity of this gauge theoretical equation. So this is a very key point. So let's do just a naive dimension count as before on general dimensional manifolds. So the number of variables is connection. So now it's a model on space of bundle valued one form. The number of equations in curvature. So this is a bundle valued two forms. But remember on arbitrary dimensions, so the rank here is a dimension of X, but the rank of two forms increase quite rapidly if the dimension of X increases. So because this is a dimension X, choose 2. Yeah. For example, if you consider 4 dimensions, so as I wrote before, so 4 choose 2 is 6. But if you go to higher dimensions, so this becomes an increase rather quickly. So this means that to write down a elliptic equation, having this, if you set this equation inside this space is too much, too many equations. So instead, we need some natural subspace of this space of two forms. For example, like this self-dual two forms in the 4 manifold settings. Okay. So this means that our base manifold need to have special structures. So it cannot be arbitrary dimensions or arbitrary or remaining manifolds. Okay. So now it comes to this picture. So this is some standard facts in differential geometry. So in this 1953, Berger gave a classification of the so-called holonomic group of irreducible closed remaining manifolds, so which are non-symmetric. Okay, so you don't need to know what is non-symmetry. You don't need to know what is holonomic group, but this anyway. I want to mention that this is the only thing you need to know is that this is a classification of remaining manifolds based on some property of it, which is called holonomic group. Okay, so okay, let's look at the list. So if this group is SON, okay, so at the linear algebra level, this is quite easy to understand. So if you have a real vector space, if you have a metric, then the linear vector space with a metric is endowed with this ON structures. If you fix the orientation of this linear vector space, so this corresponds to SON structures. Okay, so if you do this in a family, so this gives a holonomic group. Yeah, so you can understand in this way. Okay, so now remaining manifold with holonomic group in SON. So this becomes the dimension of manifold X is n dimension, and the type of manifold is called the orientable remaining manifolds. Okay, so the second type of holonomic group is the unitary group of n. So this corresponds to at the linear algebra level, you are given a complex vector space. You are given a Hermitian metric, which is preserved the complex structure. Then this data give you the this UN structures. Okay, so if you do this this compatibility with remaining metric, so this gives you the structure of holonomic group in UN. So now this becomes a complex manifold. So the real dimension is 2n, and this name is called Kähler manifolds. Okay, the third is some special case of Kähler manifolds is SUN. So it's still 2n dimension, but in this case, this is called a Calabi-Yau manifolds. So this is a special case. This is special means you can understand as a first class of the manifolds is 0. So this is, in this sense, this is special unitary group. Sorry. Okay. Okay. The next things may be less familiar to you. So the next is so-called holonomic group SPn times SP1. So this is now in 4n dimension. And this is called quaternionic Kähler manifolds, which is not quite important to our discussion. But the next is called a symplectic group SPn. So the corresponding manifold is a real 4n dimension. So this corresponds to so-called hyper-Kähler manifolds. This is also not quite relevant to our discussions. So these two remaining things are quite relevant to our discussion. So they are quite exceptional and remarkable because they only appears in some special dimensions. So it's not like before you can put n whatever positive integer you like to put here. So this only lives in 7 dimensions. This only lives in 7 dimensions and 8 dimensions. So the mathematical name is called G2 manifold and the spin 7 manifolds. So these are set here. The last two examples appear only in 7 and 8 dimension. So they are called remaining manifolds of exceptional holonomy group. So this is quite exceptional. So so what is special about this exceptional case? Okay, so let's look at this spin 7 case first. So for example, on spin 7 manifold, this distinguished. So let me not define what is a spin 7 manifold in a rigorous way, but you can understand. I can just say in one word: this spin 7 manifold is a remaining manifold such that the holonomic group is in spin 7. Okay, so this is a definition, but this does not tell anything. But the key property here is that there exists a distinguished full form on this spin 7 manifolds. So recall that if you look at this remaining geometry, so this is a manifold with some distinguished just a symmetric 2 form. So sorry, symmetric 2 tensor. This is remaining metric. So basically, this 2 tensor govern the whole remaining geometry. Okay, because this is the structure we put on manifolds. You can also put this two forms. This is basically non-degenerate two form is correspond to symplectic form. Then this is the whole symplectic geometry. Okay. Now you can understand the spin 7 geometry is a geometry about some distinguished 4 forms. Okay, it's not 2 forms or 2 tensor anymore. So you see the rank is rather big. So you can understand that in this case the geometry is quite complicated and it's very difficult to understand such geometry. But anyway, so what we need to know is the only thing is need to know is we have a distinguished 4 form, which is compatible with the remaining metric. So this is parallel with respect to Levi-Civita connection. And using this 4 form, we can decompose this 2 form based on some decomposition like this. So by some general theory, we know that there's such a decomposition where this eigenspace is defined by this. So we start with alpha is a 2 form here, then we wedge this 4 form. So this becomes a 6 form. Then we apply this Hodge-style operators. So this goes back to 2 forms. So it makes sense to equate these 2 forms with the original 2 forms. Okay, so just up to some scaling of these 2 forms. So this is equality. So the other equation is I can understand in a similar way. So you just wedge, consider star, and put a minus here. So this gives a definition of this different 2 forms. So the subindex 7 and 21 here denotes the rank of this subspace. So in a way that the space of 2 forms, so let's say the wedge 2 of this cotangent of x. So because x is a 7 dimension, so this space has this 7 times 6 over 2. So this is 20. Sorry, this is 8 dimension. Sorry, x is although it's a spin 7 manifold, but x is 8 dimension. Sorry, so this is a choose 2 is 8 times 7 over 2. So this is 28. So that means that this is a 28 dimension. So 7 means that this is a 7 dimensional subspace, and 21 means that this is 21 dimensional subspace. Okay, so this index denotes the dimension of this subspace. So now the so-called spin 7 instanton is the connection satisfying this equation. So instead of requiring the whole curvature to be 0, as I said, this on general dimension case, this is too many equations. Instead, we use this special property of these spin 7 manifolds to project the curvature to this subspace and requiring only this part to be 0. Okay, so you see that then we get 7 equations. The number of variable is 8 dimensions because the one form is a dx1 to dxa, so this is 8 dimension. So the equation is 7 dimension. So modulo gauge gives 1 dimension. So you see that this is elliptic. So this system of equations, this spin 7 instanton equation is elliptic modulo gauge transformations. So this is in the same place as anti-self-dual equations on 4 manifolds. Okay. So, and the further remark is that all above theories are reductions of these equations through this relations of this spin group. So now spin 7 contains spin 6. So spin 6 is isomorphic to SU4. SU4 is the holonomic group of our Calabi-Yau 4 folds. Okay, so SU4 definitely contains SU3. This is a dimension reduction from Calabi-Yau 4 folds to Calabi-Yau 3 folds. So now spin 7 also contains G2 manifolds, and G2 manifolds contain Calabi-Yau 3 folds. So you see that this gives from spin 7 manifold we can just inductively reduce to Calabi-Yau 4 fold story, G2 story, and the Calabi-Yau 3 fold story. Okay, so from this perspective, I want to say that 8 dimension is very special. So in my perspective, that if you want to write down some elliptic gauge-theoretical equations, the biggest dimension you can go is 8 dimension. You cannot go to any dimension bigger than this case. Okay, so this is also maybe just some funny link with this stories about infinity size. So if for the audience which are working in this string theory or whatever M theory, so superstring theory is modeled on this Calabi-Yau freeform across this 4-dimensional space. So M theory is actually based on G2 manifold across a 4-dimensional space. And this is so-called F theory is introduced by Vafa. So this actually modeled on spin-7 manifolds across 4-dimensional space-times. So you see that there's no higher theory here. This is mother theory, this is father theory. So there's no father or father anymore. So this is in my perspective, so also has to do with this exceptional holonomy of this spin-7 here. Okay, so so far, do you have any questions? Yeah, maybe they are good, go too quick or too slow.
If there is no question from the but it's not your talk is not finished, right?
Yeah, it's not finished, but maybe
okay.
it's, yeah. I want to maybe awake people. So.
Oh yeah, yes.
Because
yeah. But it's usual that the so on online seminar that the audience quite silent but listening to the talk. Yeah. So
okay.
So yeah. But anyway.
Okay.
Yeah.
So do you have any question? I think you have asked many good questions.
Me.
Yeah.
So So probably yes. So in the previous real case, in the first part.
First part, yes.
I mean, in the first part, you explained the theory in the 3-dimensional case and the 4-dimensional case.
Okay. Yes.
Right?
Yes.
And so in the complex case, the dimensions 7 and 8 were important, right?
6, 7, 8 actually.
6, 7, 8. Okay.
Yes.
So yeah. Is there any is there any correspondence? Heuristical correspondence between between the dimensions?
Yes, let me expand maybe. So as I said, so the important thing here is that we have this SU3 holonomy, G2 holonomy, and maybe SU4 or spin-7 holonomy. So this corresponds to Calabi-Yau 3 manifolds. This is G2 manifolds, and this is Calabi-Yau 4 folds or spin-7 manifolds. So this can be thought as a complexification of this ordinary real 3 manifolds. So there's no analogy here because this is not complex dimension, so it's not a complexification of anything. And this is a complexification of this real-oriented 4-manifold case. So this is some analogy or complexifications. Yeah.
So the G2 case is completely new phenomenon in the complex case.
How to say? Completely new. Yeah. Compared to real case, yes. Because this does not come from the complexifications. Yeah. What we have been discussing is about complexification of the real theory. Yeah. Yeah. But it naturally appears in these holomorphic transaminds. I wrote here.
Mhm.
In holomorphic Chern-Simons, if you look at the critical points, gradient for line, the holomorphic disk, so this equation naturally appears.
Mhm.
And I want to this page says that okay, this cannot be generalized to any dimensions. So this is quite special in lower dimensions. Low means less than or equal to 8. Yeah.
I see.
Mm.
I have another related question.
Yeah,
So,
please.
so in the case that you something is coming from the complex coming as a if something is a complexification of real thing. For
Yes.
example, if you have some Calabi-Yau Calabi-Yau threefold in the complex sense, and if it is a complexification of a real thing, then so and supposing that you know everything about real theory,
yes,
then should we think that that complexified version, the study of the complexified version reduces to the study of the real version, or is there richer information in the?
Yeah, that's a good question. So
yeah,
I think this the point here is that so first of all, this Calabi-Yau threefold is not necessarily actually a complexification of this. So this complexification is an analogy. As I said, the real-oriented free manifold means that you have volume forms like this, locally written. So the picture is I want to replace the real coordinate by holomorphic coordinate. So this means that we are dealing with Calabi-Yau threefolds. So any Calabi-Yau threefold is not necessarily a complexification in whatever sense the real free manifolds. Yeah. So a priori they are not related. Yeah, a priori they are not related. But
I see.
Yeah, but how to say? But there's some special geometry. For example, on some there's some if you start with some Calabi-Yau threefold. So there's a possibility that you can consider some involutions, such that the real locus is some real free manifolds, which maybe some Lagrangian sphere or whatever, Lagrangian some manifolds in this Calabi-Yau threefold. This is a real free dimension. So through this involution, so maybe there's a way to relate the holomorphic Chern-Simons here with the real Chern-Simons here. But this is a very non-trivial statement, and I don't think there's such a statement yet. Yeah, I think definitely it's interesting. This is interesting and important questions to explore, but it's not so easy to do this. Yeah.
I see. Thank you very much.
Yeah,
but I think it's very interesting if it's possible to connect those things. Thank you.
May I? Sorry.
No, go ahead.
May I ask one question? I'm interested in the compactness of modular space.
Say again.
So I'm interested in the compactness of modular space.
Yes.
When you consider the complex Chern-Simons on Calabi-Yau threefold,
yes,
the critical points are compact.
Yeah, that's a very good question. I will mention later.
Okay.
Yes, yeah, because this is the compactness issue is always the most important issues in this. If you want to set up the some counting invariants for gauge radical equations. Yeah, I will mention this.
Okay, thank you. Yeah.
So I was late, so I don't know my question is sensible or not. But you mentioned spin 7, which correspond to dimension 8. Does
yes.
So you said that it has a correspondence with F theory.
F theory, yes.
And then this 8 is a space dimension or space time dimension.
This is the
total dimension, or
yeah, I think F theory is a 12 dimension theory.
Okay.
Just like I don't know. Yeah, this is my naive understanding of physics. I think superstring theory is a 10-dimension theory. Usually people compactify on this Calabi-Yau threefolds.
Okay.
Yeah, so basically consider Calabi-Yau threefolds cross space-time. So because the Calabi-Yau threefold is real 6-dimension, space-time is 4-dimension. So in this sense, superstring theory is a 10-dimension theory. So similarly, you can go to M theory, which is a 11-dimensional theory. So this is model on G2 manifolds across maybe R4. If we go to 1-dimensional higher, this becomes a 12-dimension theory. This is spin 7 cross.
I see. Okay.
R4. Yeah.
Okay. Thank you. Thanks.
Yeah. Is there any other questions? Yeah, maybe not. So yeah. Here I want to ask question because quickly I will come to some technical point of algebra-geometry. So yeah, I may lose more people. Sorry. Okay, the questions are related to Masaki's questions. So can we make the above pictures mathematically solid? Okay. So this is actually a very difficult question because Yang-Mills connections usually blow up at codimension 4 locus. So this means that when the base manifold is bigger than dimension 4, so there's no good understanding of it because so in the real 4-dimension case, the blow up locus is just 0 points. So to understanding this is not so difficult. But if the dimension gets bigger and bigger, so it's difficult to describe the locus where this degenerate, because such locus is usually not necessarily even continuous. It's very bad actually. You need to use some machine called the geometric measure theory to describe such a set. Okay, so this blob locus is some set, maybe have some finite Hausdorff dimensions. So this is quite bad things even from the perspective of continuous function or smooth function. It's very bad. So people actually don't understand the compactification of such gauge-theoretical moduli space in high-dimensional where. So now the trick is that also the link with algebra geometry is that on even dimension, so we may use algebra geometry to help. So now my focus here is on 8 dimensions, so the biggest dimension. So then the setting of spin 7 manifolds plus the restriction to algebra geometry setting gives you the constraint we have to work with Calabi-Yau fourfolds. Okay. So recall earlier we discussed this complex anti-self-dual equations on Calabi-Yau fourfolds. So this is some complex analog of anti-self-dual connections on 4 manifolds. But now it's on Calabi-Yau fourfolds. Okay, so there's a closer cousin of such equations, the so-called holomorphic Hermitian Yang-Mills equations, where the first equation is basically the 0-2 part of curvature is 0, and the second part is still the same, the moment map equations. So obviously, so the solutions of the second equations is the solution of the first equations, because if this is 0, definitely if you apply this star 4 operator, which is a non-degenerate, so this is 0, and the whole is 0, obviously. So definitely because we want to link with algebra geometry, so we want to find a condition that these two solutions maybe they're the same. Obviously, a necessary condition is that the Chern character of this bundle we start with should be of Hodge type, should be 2-2 type. This is because if we start with solutions here, then if we want this solution also satisfying this equation, so this means that this D bar A already defines the holomorphic structures on the bundle. So these equations means that this connection defines a holomorphic structure on bundle. Okay, by the standard this characteristic class theory, we know that the Chern character has to be of Hodge type. So this is something well known in this characteristic class theory in complex geometry. So what's more important is that actually, this is a sufficient condition. So you say that by some characteristic class argument I mentioned before in this on the setting of a real 4 dimension. Remember, you consider truncator of second truncator of this bundle. So this is on real 4 manifolds. So this equals to the trace of FA square up to this constant. So on Calabi-Yau 4 folds, you can consider this integrate of this second truncator of E wedged with the holomorphic volume form. This is a 4-0 form. Then this becomes a trace of FA square wedged with the 0-2 forms. So this is a topology. This is 0 because this is 2-2 type. This is 4-0 type. But X is a Calabi-Yau 4-fold. So this is 0. Now this is a 4-0 form. So this only contributions comes from the 0-2 part of this curvature. Then you can further decompose using these self-duality operators to write in the plus part and minus part. And you can easily see that under this this setting, these two systems of equations have the same solutions. Okay, this is not a bad condition because this is exactly the setting of complex geometry or edge geometry, because the setting we start with is already holomorphic. But this is not the condition anymore. Okay, so then we also need to note the following deep theorem by Donaldson, Uhlenbeck, and Yau, which says that if we consider the moduli space of holomorphic Hermitian-Yang-Mills, the solution of holomorphic Hermitian-Yang-Mills equation, then this moduli space is the same as the moduli space of slope-stable holomorphic bundles. Okay, so recall that what is the notion of slope stability of a holomorphic bundle is as follows. So given a holomorphic bundle E, so we want to test all the slope of all the subsheaf of this bundle. So consider a non-zero proper subsheaf of this holomorphic bundle. So if you are not familiar with sheaf theory, you can just pretend that F is a subbundle. Then we can consider the first class of this sheaf wedged with this third power of Kähler form. Then this becomes a 8 form. Then we can integrate on X. So this is usually called the degree of this sheaf. Then we quotient down the rank of sheaf. This is called the slope of this sheaf. Then the condition of slope stability is that any subsheaf we should have this strict inequality. Okay. So now through this Donaldson-Uhlenbeck-Yau theorem, we see that this moduli space of solutions of Hermitian-Yang-Mills equations has a compactification, has a discretion by complex and algebra geometry. And in here, there's a powerful tool of compactification by adding so-called Giesecke-Maruyama semi-stable sheaves. Okay, this is something I wrote in a one sentence here. So it has a natural compactification by Giesecke-Maruyama moduli space of semi-stable sheaves, whatever it means. So it has some nice algebra-geometric compactification. So this means that in the algebra-geometry setting, the moduli space of solutions of this complex anti-self-dual equations we are interested in has a compactification by using algebra-geometry. Okay, so this is the way we tend to help from algebra-geometry. Okay, so this is not the end of the story. So the remaining issues to defining the counting invariants is the following. So there are two issues. There are so-called the transversality issue and the orientability issue. So this is the technical part. So the transversality issue is basically deal with the singularity of moduli space. So unlike the moduli space of objects in low-dimensional manifolds, so moduli space of sheaf or bundles on Calabi-Yau 4 folds is very, very degenerate. It's very complicated. For example, the moduli space can look like this. So it has some two-dimensional components, It has some one-dimensional components. It has some two-dimensional components where we have some non-reduced scheme structure. This can also be non-connected. Rather bad. Okay, this can be the moduli space. So how can you do accounting on such a moduli space? Okay, so this is need to use some technology to achieve these transversalities. Okay, so I will mention later. So the second issue is about the orientability. So the orientability is to deal is after this transversality basically. So let's say we can achieve the transversality, and let's say the moduli space becomes 0 dimension. This becomes let's say the moduli space is finite number of points here. So how can we count this number of points? So usually we need to assign some natural signs to each point. So for example, this is a plus sign, this is a plus sign, this is a minus sign. So total sum is will become something interesting, something invariant. So in this case, this is the invariant is 1. So this orientability issue in physics language is also called anomaly cancellations. Okay. Basically, you need to deal with the determined line bundle of certain certain Dirac operators and show that the determined line bundle is trivial. Okay, so let's go to the technical part, the first issue. Let me just give you an explanation of the rough idea of this. So the thing is that we need to study the so-called deformation obstruction theory of sheaves. So what this means? So the meaning is that this so-called coordination model for this moduli of bundles or sheaves. So it says that we have a first order deformation space parameterized by x1 EE. And we have a obstruction space parameterized by x2 EE. So there's some distinguished algebraic map or holomorphic map kappa, such that the zero locus of this map is isomorphic to moduli space locally. Okay, so this is the moduli space of sheaf or bundle, whatever we are interested in. So this is local isomorphisms. So in a way that although the moduli space, okay, is maybe constructed by some abstract tool like the geometric invariant theory, but the local structure can be described this quite clearly by this local coordination model. So this is a finite dimensional vector space. This is a finite dimensional vector space. This is some polynomials maybe. And the zero locus describe the moduli space locally. Okay, so remember we are in the Calabi-Yau setting. So the Calabi-Yau setting says that we have a set duality on this x2 of EE. So this gives this vector space a non-degenerate quadratic form, okay, which means that we have ONC structures. So there's a homotopy equivalence between ONC and the ONR, which means that we can find out some positive real form of this quadratic vector space. This is a vector space with a quadratic form. Then the right model we should look at is we consider this decomposition based on this choosing of real forms. Then we consider the composition of coordination map kappa with this projection. So this will become the right local coordination model for our complex anti-self-due moduli space. Then the way is that we perturb this kappa plus to intersect the zero section transversely and then glue such local models. Because as I said, this zero locus is the moduli space. So the moduli space is complicated because this kappa, the graph of kappa does not intersect the zero locus of this. That does not intersect this x1 in a cleaner way. So let me draw a picture. So this is a x1. This is a vector space. So this is a vector bundle x1 cross x2. This is a trivial vector bundle with fiber x2. And we have this trivial bundle. And we have a zero section here. So our coordination maps give us a graph of such this vector bundle. And because this graph intersects this zero section in a non-generic way, so this means we get the complicated moduli space. Okay, there's a zero section, zero locus here, describe the moduli space here. So the way is that we motivate by Euler class construction. We perturb this section slightly to make this transverse to the 0 section. Then the intersection will become very clean, and this becomes finite dimensional manifolds. So this is the way we achieve transversality in this setting. Okay. So anyway, this is local model. We need to glue such local models, and then make the make some global defined cycles in the moduli space to integrate. Okay, so so this is a rough idea, but actually to make this work is rather technical. So this is some technologies, so-called virtual fundamental class. So, okay, so the next is the orientability issue. So we consider the super determinant of this deformation obstruction. So we have x1, x2 plus. Basically, we consider the determinant of the target over the determinant of the domain. So at each point, this is a line, but by index theory, family index theory, this is forms a real line bundle on the moduli space. Okay, so the point is that we need to show that this is a trivial line bundle. So this is anomaly free conditions in physics language. So actually, this is true for any Calabi-Yau fourfolds. So altogether, we cook up some virtual class in our moduli space. So this is some you can understand this as some manifolds in the moduli space. Sorry, these are some manifolds in the moduli space of some constant dimension. Okay, so this dimension is called the virtual dimensions. So which can be computed by Riemann-Roch here. Anyway, if the truncator of the sheaf or bundle is V, so this virtual dimension is given by this 2 minus chi VV. So this is the Euler pairing here. So anyway, I want to say is that so this is topological. It does not depend on the specific bundles or sheaves you pick up. Okay. So although the moduli space may look like that, but we can construct some constant dimension cycles inside this moduli space, which gives you the right things to look at. Okay. So for example, if this virtual dimension is 0, then we can just count the number of points here. Then this gives you some Donaldson type invariants for this Calabi-Yau fourfold settings. Okay. So in general, if this is a virtual dimension is positive, you can put some insertions to integrate. So in physics language, you put some observables to integrate to do your path integral. Okay. Okay. So another advantage of this algebro-geometric setting is that we can consider more flexible moduli of sheaf, which may not contain any locally free sheaves in our moduli space. For example, if you consider the ideal sheaf of subschemes, 0-dimensional subschemes, this is not locally free anymore. So it does not correspond to any bundles anymore. Okay, so this, but in physics language, maybe you can understand this as some D8, D0 branes in Calabi-Yau fourfolds. So there's some points here. So outside these points, this is just a trivial bundles, but there's something non-trivial happens in this point. So in geometry, there's a way to describe this called ideal sheaf, 0-dimensional subschemes. Okay, so finally, very quickly, I want to, because I promised in my title that I want to link with individual geometry. So I think later in a talk or in a planned coffee meeting talk, I will give a quick explanation of individual geometry. But let me do it very quickly, even quicker now. So in individual geometry is quite natural objects because counting actually is one of the first several things we learn in our infancy. So when we become something, it becomes identity in this world, the first several things we did is counting. So individual geometry is counts geometric objects or structures on geometric spaces. So I'll give several examples here. For example, in the real plane, in the real R2 plane, you consider 2 points which are not the same. You count the number of lines crossing these 2 points. So we know that by this Euclidean geometry, there's only one. So the number of lines passing through two different points in R2 is one. So more non-trivially, you can consider this case. I can consider the number of lines on a qubit surface. So this P3 is actually a CP3. Anyway, so this is some complex algebra variety. And consider degree 3 hypersurface in these things. This is a qubit surface in P3. And the number of lines here is exactly 27. Okay, there's also some famous stories in algebra-geometry. And another example is the number of conics, which is the degree 2 curves in P4, which sits in X. So X is a quantity threefold here. So this quantity threefold, you know that this is famous in string theory because this is a Calabi-Yau threefold. So at least the number of quantics here is very big numbers. So in this perspective, our theory counts stable coherent sheaves or complex antiseptic connections on Calabi-Yau fourfolds. So let me give you a relations maybe to see how this links to curve countings or string theories. So this in mathematical language is called Gromov-Witten theory. So let's consider the moduli space of genus G unpointed stable maps from a curve of arithmetic genus G to our Calabi-Yau fourfold X. So we put some mark point here in our domain. So in pictures like this. So maybe this is some curve. We have some mark point. We consider the space of all holomorphic maps like this. These are Calabi-Yau fourfolds. So we fix some topological data such that the push forward homology class, the push forward fundamental class of this C should be some distinguished fixed curve class in ambient Calabi-Yau fourfolds. So in this case, as before, so this moduli space is very complicated, but it has a virtual class of some virtual dimension. So in this case, this is can be computed by Riemann-Roch. This is 1 minus G plus N. So for example, if you consider genus is bigger than or equal to 2, so there's no holomorphic curve anymore. So that means Gromov-Witten theory for genus bigger than or equal to 2 is trivial on Calabi-Yau fourfolds. So there's only two cases to consider, genus 0 and genus 1. So let's consider genus 0 first. So we consider genus 0 one-pointed stable maps. So where an element here is a map from curve to X, so we have a map point. So we have so-called evaluation map to X, which evaluates this F at this point, okay, which in X. So this is well defined. So through this map, we can pull back homologic class on X to the moduli space and integrate on virtual class. So this counts some let's say our X is some complicated Calabi-Yau fourfolds. This counts maybe a rational curve, which are passing has some incident conditions with some cycles defined by gamma. This is the naively understanding of this counting. So by the Gromov-Witten theory, we know that this is a rational number. So they are not integers because this moduli space has automorphisms. So similarly, you can consider genus 1 theory, which consider genus 1 stable maps. If you look at this formula here, this is already 0. So we don't need to put any map point. So we can just integrate 1 here and get rational numbers. Okay, this is genus 1 invariance. So an interesting question is that, okay, Gromov-Witten invariance suppose count curves on Calabi-Yau fourfolds from this mapping perspective, sigma model perspective. But how can you count curves how can you count something to end up with rational numbers, but not integers? So this is quite mysterious part, quite ridiculous. So it's important to understand the integer curve counting because that's a real count. Okay, so there's a distinguished conjecture by Clem and the Panda in 2007. So not very old story. So they proposed to define two sequences of numbers, n0 beta gamma and n1 beta, in terms of this Gromov-Witten invariance. So let me just explain the first equalities. So the left-hand side is the genus 0 Gromov-Witten invariance we defined by this theory. So the right hand side is a sum of all k which divides beta. So this divides means that I consider a positive integer such that beta over k should be an integer valued homology class. So this is an integer value. So there's only finite number of such k's. And then I put a 1 over square k square here. Then I put something I want to define here, n0 beta over k. Okay. So this suppose to give the definition of n0 beta because by something so-called the Mobius inversion formula. So you can do the Wikipedia search in this Mobius inversion formula. It tells you that if you define something like this, then you can read off n0 beta indirectly by the information of the left hand side. Okay. So similarly, you can define the n0 n1 beta by the genus 1 information and something related to genus 0 information, but I don't want to go to details here. So anyway, through some complicated manipulation, we end up with two things, n0 beta and n1 beta. Okay, so their amazing conjecture says that they are integers. So it's quite amazing because so you see that Gromov-Witten invariants are rational numbers, and then in here there's some complicated rational numbers which may appear as here if you do these expansions. So it's interesting to see to understand this conjecture actually. So how to say? So in their paper they proposed this definition and they compute a lot of examples of Gromov-Witten invariants. And through their formula they can literally see, okay, all this n0 beta, n1 beta they define are integers. So they do a lot of checks of these conjectures, and I want to say that this is a very convincing conjectures. Okay, so in our talk, let's call this genus 0 and genus 1 Gopakumar-Vafa type invariants of Calabi-Yau folds, because the similar parallel stories on Calabi-Yau folds is called Gopakumar-Vafa invariants or BPS invariants, or whatever it means. So okay, how this links with our gauge theory setting? Yeah, sorry, I think I'm already run out of time for 10 minutes. So yeah, maybe let me quickly give the last two pages.
So how many?
Just 2 pages.
How many minutes will you?
Just 2 or 3 pages.
I think it's okay.
Yeah. Okay.
So,
sorry for this.
Yeah. No, it's okay. Yeah.
Yeah. Okay. So let me quickly do this. So okay, we consider some moduli space of so-called stable pairs. So this you can understand as some framed degenerate connections. So now F is a one dimension, so-called pure one-dimensional sheaf. You can understand this as some vector bundle on some maybe line bundle over this some curve, support on some curve. And the OX to F, this is a section of this sheaf, or in each support curve, this is a section of this line bundle. So literally, this means that we can consider section of line bundle, and the Z locus is some points in the curve. Okay, so the condition is that we require the co-kernel to be zero-dimensional. Anyway, so this co-kernel is this point here. This is some technical definition, but you can just understand this, that moduli space is some framed line bundle on some curve with a framed connection or something like that. Okay, so this gives the curve class of this support curve, and this gives the Euler characteristic. So we need to fix some topological data. So by our discussion, we have some virtual class of certain dimensions. Now in this case, it's 2n. Now you see that I need to put some insertions because this is not necessarily 0. So the insertion we put is like this. We consider moduli space P, and we consider X. We consider their product, and we consider the universal object here. So this sheaf, there's a family of these objects on this moduli space cross X. There's some universal one-dimensional sheaf. Then what we do is pull back a cohomology class. We couple with the certain truncated of F. Then we push forward to P. So this defines some insertions on moduli space. Then we just integrate the nth power of this insertion. So this gives you some integers. So different from Gromov-Witten theory, these are integers because because our moduli space is some nice space. It's not a Riemann stack or whatever. There's no automorphism here. So this is the advantage of doing gauge theory or this shift theory. Okay, so now I want to stay conjectures here. So the conjecture says that the left hand side we form a Jenkins series of this stable pair invariants. We call it stable pair invariants. So this Q and T, they are formal variables. Just to label the discrete data n and beta here, we just form Jenkins series for convenience of forming Jenkins series. So n factorial here is just normalizing factors, not so important, important here. So the left hand side is a summation formula, and the right hand side is a product formula. So it's a product over all curve class, and for each fixed curve class, so it's two parts. The first part is the exponential, where the power is the genus 0 Gopakumar-Vafa invariance defined by Clem and Panda. And the second is the power is the genus 1 Gopakumar-Vafa formula invariance. So now the base of the second part is more complicated because it involves so-called Markman-Holm functions, which counts 3D Young diagrams or plan partitions. So the first remark is that this gives some, naively speaking, this gives some string gauge string dualities on Calabi-Yau fourfolds because the left-hand side is some sheaf moduli space or gauge theoretical moduli space, the invariance we get. But the right-hand side is some invariance we get from Gromov-Witten theory or just a 2D sigma models which are related to string theories. So the second remark is that if you admit this equality, so the integrality of the n0 beta and n1 beta is automatic because our invariants are integer valued. So finally, I want to say that the way we write down this picture, we write down this equality is based on certain ideal geometry. In this certain ideal geometry, we can compute everything and prove this formula. But this ideal geometry cannot be achieved in the setting of ideal geometry. So it's not a rigorous proof. But we verify in several examples of our conjectures. So anyway, I want to say that this is some maybe convincing conjectures interesting for further studies. Okay, I just stop here. Sorry for the delay. Yeah.
Yeah. Thank you very much for a very nice talk. And
yeah, thank you very much.
Yeah, I enjoyed it very much. And so, is there any question from the audience?
May I ask a question?
Yeah, please.
I have 3 questions. So the first question is related to the physics. So
yes,
Witten showed Donaldson polynomial invariant can be realized by a partition function of topological twist of some Tsuji theory. So I want to know
topological theory of what?
A topological twist at Donaldson polynomial invariant can be realized by a partition function of some field theory.
Yeah, I think this is Witten's work, yes.
Yeah, so I want to know, is there a corresponding field theory for complex version of Donaldson invariant?
Yeah, I think many years ago, even before this series, so now the Calabi-Yau 4 theory is recently defined, just inside within these 5 years. I think even back to 1996, I think there's some papers by somebody staff from Bollywood or something, someone. Bollywood or singer or another, maybe there's another Japanese physicist. Sorry, I cannot recall his name. I think they discussed the path integral approach to this spin 7 instant on counts or something.
Oh, I see.
Yeah, but I'm not sure how much they achieve. Yeah, for example, can they show that this is a topological invariance or something? Yeah, this is, I'm not sure. Yeah. So may I ask why you are interested in this question?
Yeah, physical interpretation in the Donaldson theory, physical interpretation implies, for example, the Calabi-Yau equation appears
Mm.
in the setting. So the natural equation is there such a corresponding equation? And Calabi-Yau equation has very nice compactness.
Yeah, exactly. Yes.
Yeah.
I think these questions, I think many people ask similar questions. Yes. I think, in my opinion, I don't think there should be Sepel-Witten type equations on Calabi-Yau fourfolds.
I see.
Yeah, this is because of the following. So first of all, I think the origin of Sepel-Witten equations comes from mathematicians actually. They are not the story is not like okay, Witten someday he just study his topological trace and consider this come up with Sepel-Witten equations. But the story I know is that so he's highly motivated by the work of Kuhlheimer-Moroka. So you know that in Kuhlheimer-Moroka they show that there's some basic classes of which determines the Donaldson invariants by some basic data called basic classes, some distinguished they could distinguish homology two cycles. I think this Witten tries to understand Kuhlheimer-Moroka's theory. Then he just came up with this theory. So this is the first thing. The second thing is that the reason I don't think there should be a Sepel-Witten type theory here is that so you know that I think the real power of Donaldson theory is that it works on any real-oriented close-oriented four manifolds. For example, if you look at the Donaldson invariants on Kähler surface of general type, I think the invariance is rather trivial. Yeah, you only had non-trivial invariance in this canonical curve class. I think the invariance is just a +1 or -1. Sorry, the Sepel-Witten type. Sorry, Sepel-Witten, not Donaldson. Sepel-Witten invariance. So in a way that I think the I think the real complication of Sepel-Witten invariant, Donaldson invariance is that it makes sense on any real four manifold, not necessarily have complex structures or Kähler structures. So this has many advantages of doing these four-dimensional topologies. Yeah. So for example, if you consider Calabi-Yau fourfolds and you can consider this line bundle, maybe with sections. Yeah, I think this does not contain much information. Yeah.
I see. Yeah, thank you. I see.
Yeah.
And the second question is related to the quotient singularity of the modular space. So in the Donaldson theory,
yes,
we need to assume the condition B plus is greater than 1.
Yes.
And then we can avoid the quotient singularities.
Yes.
And when B plus is equal to 1, there is some wall crossing phenomena.
Yes.
So I want to know is there a corresponding phenomena for complex version?
Yes. So as I explained just in this talk, so you see that this H2 of so can you see this?
Yeah.
H2 is should be replaced by H02, and H2 plus should be replaced by H02 plus. So in this case, if you consider Calabi-Yau fourfolds, so how to say? So this is some known fact. Known fact is that let's say the X is a Calabi-Yau fourfold. Let's say the holonomic group is a strict SU4. So this is there's no reduction to Calabi-Yau threefold across C or something. Then H02 of X is 1. So this means that the H02 plus is also 1. Because this is complex dimension, this is real dimension. So this means that the Calabi-Yau fourfold setting is always, you can understand it as correspond to H2 plus, which is 1.
I see.
Yeah. So there's no theory for H2 plus, which is bigger than 1. So there's always wall crossing.
I see. So the invariant depends on the choice of metric.
No, it does not depend on. So on four manifolds, this this does not depend on metric. So on Calabi-Yau fourfolds, a priori you start with you need a metric, you need a complex structure, but in the end you show that this is deformation invariant. So it's invariant under deformation of complex structures.
But it depends on the choice of a word, right?
But how to say? Yeah, I think this is something different. So deformation invariance means if you deform complex structure, the invariance does not change. But the word crossing things I have in mind is that you change the parallelizations, because in defining this modular space, you need to choose ample line bundles.
I see.
Yeah, you need to choose basically choose a Kähler. You need to choose a Kähler class.
I see.
So this Kähler class, if you deform the Kähler class, so it may change. Yeah, but if you deform complex structure, it does not change.
I see. Thank you.
Yeah.
And third question is related to the structure theorem of Donaldson invariant.
Yes.
So the structure theorem relates the A3 modular space of different bundles.
Yes.
Different Chern number. So
yes.
So I want to know, is there a corresponding structure theorem for the complex version of the Donaldson invariant?
Yeah, at this moment, at this moment, there's no such theory.
I see.
Because yeah, I think originally in full manifold case, this is achieved by analytic method, right?
Yeah, they consider some singular connection. Yeah, and so maybe there is some corresponding objects in dimension, higher dimension.
So sorry, can you say again question? Do you mean the degeneration formula or gluing formula?
No. The structure theorem, which relates so Kronheimer-Monod structure theorem, which relates.
Okay, I see.
Different instant numbers.
Okay, I see.
Yeah.
I think this case is a little bit complicated because on real full manifolds, usually you consider SU2 or SUN case. Yeah, anyway, let's say SU2. So in this case, the only choice you make is the C2 of the bundle, which you refer as instanton numbers, right?
Yeah.
But yeah, this is because the first Chern class is already 0, and so there's no higher Chern class because this is a full manifolds, so this is 0.
Yeah, that's right. Yeah.
Sorry, it's free. But on Calabi-Yau fourfolds, it's more different. So you have Chern 1, you have Chern 2, you have Chern 3, you have Chern 4, you have Chern 0.
I see.
So this is in H even of X. So if you want to say instanton number, you have to fix which Chern character you mean.
I see.
So it's more complicated because geometry is more complicated. On full manifold or algebraic surface, the only algebraic geometry object is just divisor, just a curve or some points. But now on Calabi-Yau fourfolds, you have divisor, you have surfaces, you have curve, you have points. You have more complicated geometry.
I see.
Yes. So it's at this point, so I think it's there's no such generalizations.
I see. Thank you.
But it's definitely interesting and important to understand such. Yes.
Yeah, thank you very much.
Yeah, thanks.
Is it okay? I thought you have 3 questions, but
He already asked the 3 questions.
3 questions. Okay. Sorry. I misunderstood. But yeah, it's nice that anyway. So I have my question, but maybe I will ask it later. So if because it's a bit late now. So if is there any question from the audience? Maybe not. Yeah. So maybe you can ask in the drinking party or So okay. So
sorry.
Okay.
What is the question?
No. I didn't ask any question. So
So
even though somebody has questions, they can ask in the drinking party if
Yeah,
they
yeah, sure,
want.
sure.
So
Sure.
yeah, okay. So let's close the seminar for now.
Okay.
So thank you. Let's chance to speak again.
Yeah, thank you very much for joining.
Yeah. It was very enjoyable. So yeah. So okay, I will stop the recording now.
So it's okay. So it's recorded. Okay, and yeah, I want to watch the first part. So